I ordered some things from the UK firm Kitronik, so they had a clearance section, so I bought a couple of power plugs, which were always useful. But the main thing was this kit here, so this supercapacitor kit. So it's quite a simple kit, but it looks like it might be entertaining. I've wanted to play with supercaps for some time, and you see it comes with quite good instructions, very thorough in fact, compared with the sort of normal Chinese things that I put together. So we have a schematic here. So basically the core of the kit here is the LM393, which is a comparator. So there's two voltages have been set on the inputs there, two threshold voltages, and when this input voltage from the supercap reaches the two thresholds, it's going to light these two LEDs one after another. So basically the LM393 is allowing us to charge the supercap and see when it's fully charged. And then there's also a switch, so once the supercap is charged we can flip the switch and we can power something with it. So it'll be interesting to see what we can power, see if we can power the Microbit, for example, using the supercap. So the thing that's really amazing about these supercapacitors is the huge capacity, the huge amount of capacitance for such a small thing. So this is, you know, a capacitor which is really physically no bigger than some of the big electrolytics. So like a standard electrolytic capacitor might be, you know, like 100 microfarads or even 1,000 microfarads, which is still only a millifarad or a thousandth of a farad. But this is actually a 1 farad capacitor, even though it's really only like a couple of coins stacked up one on the other. And they do this with you know, so these sort of supercaps have only become available in the last few years in this sort of size, and it's because of material science, the improvement in material science, and they very cleverly managed to make the plates have a bigger surface area and squeeze them really very close together, so the plates are very close together, both of which things really increases the capacitance. So you end up with a very compact capacitor that has a really huge capacitance value, and one farad is really a lot of capacitance to have in one unit. So I'll solder these things in, and then we'll get started with the testing. So we've got all the different resistor values here. So usefully these are all using the three band colouring, which I can read quite easily. I'm not so good at reading the 4-band resistors. So these are two 10 ohm resistors. We've got 68k, 10k, that one's 15, so 15k, and then these are 2 times 470 ohms. So I'll fit all the resistors first, as is my convention, and then we'll see what to put in next. Okay, so R2 is the 15K. R3 is 10K. It's interesting that they've chosen to have all of the resistors down the centre of the board, so they've laid it all out with all the resistors parallel. Obviously they didn't need to do that, but I mean, it makes sense for some of the resistors to be close together because they're forming a resistive divider for the inputs for the comparator. Go and find some snips in a second. It's quite difficult working around these leads sticking out. That's better. Right. So R4 is a 68K, which is that one. R5 and 6 are 470 ohm. We've also got a diode there, D1, which is this fella. I don't think I've ever seen a blue diode before. Make sure I get it the right way around. Okay, that's all the resistors in place. Now the IC goes into a socket. They very kindly provided a socket, so I'm going to put that in. Okay, that looks good. Now maybe the LEDs. So the LEDs, they're shown with a flat on one side on the silk screen, and I can't remember whether it's the anode or the cathode, but there is a flat. You can see, if I can get that to focus, there is a flat on the side of the LED, so you can use that. I think that must be the cathode, because the anode, I remember, is always the long lead. I'll just tack one leg in place here to try and get the positioning right. There it goes, nice and flat against the board. Now I've not seen one of these before. That's quite neat actually. So you can solder in these little pins, and then the actual bit of the power connector with the screws on it just plugs in on top. Okay, so we'll put the switch in also. That fits nice and snug. Doesn't really want to solder. Don't know what's going on there. Maybe I need to clean the leads of this switch. Oh, it's hot. I might just buff that with some sandpaper. Right, let's give that another go. Well, that's really resisting. Maybe it's because of the thermal mass of the switch. That's gone now. That's good. Just need to heat up the body of that switch, I think. Yeah. It's a bit blobby there on the top. If you see that, it's really rather too much solder on there. I might get the solder sucker out in a minute and clean that up, but the actual contacts of the switch are good. So we've got the cap that has to go in there. It is polarized. You can see the pluses on one side here and minuses here. And the minus is marked on the edge of the cap there. Got some minus symbols. Make sure we get that the right way around, because capacitors wired the wrong way around can produce a spectacular amount of smoke. One thing that's interesting is these supercaps are often really low voltage. So this one's rated at 5.5 volts. So this is going to charge up from a USB interface. So they give you a USB lead with the two wires, just the plus 5 volts and ground. So this is going to charge from a USB port, which is nominally 5. I think the top value is 5.2 volts. So this cap is rated just a little bit higher than 5.2. But these super caps, I've got a few in my parts box, which I might get out and show you in a minute. But they're invariably low voltage, so that's, I don't know why that is, but it's obviously something to do with the way that these things are constructed, that they make them with the minimum voltage level possible. Right, and so these so the charging wires are going to go in here, and then this is the output here. It's marked motor, so I'll find some wires to stick in there as well. Right, so the switched side is negative, so I'll put my green wire in there. And then all that remains is to install the LM393. So I do have an IC inserter somewhere, but these 8-leg ones you can usually do by hand. Or, having said that, it doesn't seem to have gone in very well. There we go, that's all right. In the right orientation, and all the pins are nicely engaged in the socket, so we're ready to test. Right, so I've plugged it into this bit of board here so that I can connect it to a motor, and I've got a power bank here, so we'll try and charge it up, see what happens. Not sure which position the switch needs to be in. Just have a look at the voltage here. 300 millivolts. Right, so I think it needs to be left for charging, so I'll plug that in. Alright, so the first LED has come on now, so it's reached the first threshold. So the supercap's partially charged now. It's actually, I remember looking at in the schematic, it's charging through a 10 ohm resistor. So so that's limiting the current, and it takes a bit of time to to get the charge into the supercap. Let's see if this other LED's going to come on now. There we are. So we've got 2 LEDs, so that means it's charged up. So we could check the voltage on the cap. Shall I unplug this? We'll just measure directly across the cap here. .5 volts. So it's charged up to 3.5. So let's try connecting the motor. So I put a little mark here so that you can see the motor when it turns. Right, so if I switch this on, it should start turning the motor. There we go. It's running the motor. I'm not sure how much voltage this motor needs. It's just one I pulled out of a box of bits. I think it came out of a tape deck or something. Not sure. Let's try and read the voltage. There you go, 2.5 volts. You can see the voltage is decreasing, so the supercap is discharging through the motor. So the motor's the load. There's no resistor in series, so this is literally dumping all of the energy out of the supercap directly into the motor. It's getting a bit slower as the voltage goes down. Not sure how long this, what voltage this motor runs down to. Seems to be doing quite well. It's below 2 volts now. The motor's still going. But modern motors are quite amazing, really. They seem to run on very low voltages. It's below 1.5 volts now. Can hear it getting slower and slower, approaching 1 volt. So look at that, the motor's still turning even below 1 volt. It's getting really slow now. Let's see when it finally stops. That was the meter beeping at me. So below 0.5 volt. Still turning. .300 millivolts. Oh, it's finally stopped. So we're now in the 200s of millivolts. Really not much charge left in the cap now. So I've just charged up the supercap again, and I thought I might try running the Microbit off off the supercap. So if we measure the voltage on the cap, sorry you can't see the multimeter, but that's reading about 4 volts. So it should run the microbit without any difficulty. So we'll put the red wire on the positive and then the green wire for negative. Whoops, just fell out. Red wire, green wire. Oh, need to flick the switch first, don't I? Green wire, and there we go. So I'm not sure exactly what software I've got running in my microbit, but it's obviously writing a 0 to the display. So you can see that you can actually run a you know, Internet of Things device from a supercap. So that would be useful for you know, running a portable device for a short amount of time. I'm not sure how long this will run off the supercap. Or of course you could use the supercap as you know, sort of power outage, you know, emergency power supply to just keep something running for a little bit after the main power has gone off. Anyway, so a genuinely useful circuit for powering devices like this. So to explain how this circuit works a little bit, so obviously the central part is the dual comparator, the LM393. So what we've got here is a network of resistors which is creating two voltage levels here. So if you work out the split across these resistors, what you see is that this wire here will be at about 75% of the input, 5 volts, and this one will be about 85% of the 5 volts. So then you've got the A minus pin of the comparator is at 75% and the B minus is at 85%, and then the other pins of the comparator are connected through this 10 ohm resistor to the top of the capacitor. So this is reading the charge level of the supercap, so the voltage level of the supercap. And so when this voltage gets past the 75%, that will mean that the B comparator will trigger and this LED 2 will come on. And then when the supercap gets to 85%, it will trigger the A, is that right? The A, no. So the A is at 75%, and then the B is at 85%. So when this reaches 85% of the voltage on the supercap, then you'll get B that triggers, and then that will make the other LED light up. So it's a very simple two-step you know, sort of charge level indicator basically. So you can see the switch here. So the switch would be in this position for charging, which means that you've then got the 5 volts through the 10 ohms, which limits the current, and the D1 diode, which stops the capacitor from sending its charge back into the USB. So this is the charge path through the capacitor and then back through ground. And then of course when you put the switch in the other position, you've got the supercap is basically wired directly to the output, so it's then delivering all of its charge direct to these output pins. So it's quite a simple circuit, but very effective, and an interesting illustration of what you can do in terms of storing a lot of useful charge in a supercap.